Okay, so today we're going to start our second order methods unit. I'll just briefly flash up a histogram of the little test 1 scores. Hopefully that was not traumatic for everybody, and you took my word for, we're just trying to give you kind of manageable questions. I think the histogram definitely reflected that. People seem to do quite well overall, so that's the histogram of scores. In case you're curious, the mean I think was about 24.5 or something like that, around there. And it's out of 35. So yeah, people generally did well. And I guess we might post the statistics on Piazza if that's helpful for people to see. So, all right, I don't know what else to say, but yeah, hopefully you guys kind of could found that most of the questions are reasonable. If somehow you think that the questions were really confusing, please come talk to me, because I think then we need to kind of situate where you are in terms of your understanding. So just come talk to me if you didn't find the test to be all that manageable. So today we're going to talk about Newton's method. We're starting our second order methods unit, and this is our last kind of I don't know what to call it, but maybe like standard or classical unit in the course. After this unit, we're going to do a bunch of stuff that is more timely and more advanced. So we'll talk about optimization methods that are newer and maybe popular, like in today's climate. Everything we've learned so far, I think, there's been a focus on machine learning and statistics and application, but the methods themselves have been fairly classical. And same with the theory we've discussed. And okay, so this is the last kind of unit in that classical part of the course. So I'll just remind you what we did last time. Last time we talked about duality, and we talked about these things called conjugate functions. And we tried to connect parts of duality we learned in previous courses to conjugate functions and other kind of useful notions that we call dual correspondences. And these conjugate functions they're a very handy tool. They're defined as follows. If you give me a function f, its conjugate is defined at a point y by the biggest difference we can make between y transpose x and f of x. And it's always convex regardless of the convexity of f to begin with. Okay, that's just because this thing, if I look at it, if I fix x and look at this as a function of y, it's just affine, so it's convex in y, because it's just affine in y. And so if I take a max over all x, the resulting function is still convex. We saw things like when f is a quadratic, f star is a quadratic. When f is a norm, f star is the indicator of the dual norm unit ball. And we learned this rule here, that when f is closed and convex, there's this very handy relationship between subgradients of a function and subgradients of its conjugate. If x is a subgradient of f star at y, then that's true if and only if y is a subgradient of f at x. We're going to actually revisit this a bit later in the course when we talk about ADMM and dual decomposition. We're going to see this is an extremely useful fact algorithmically. And okay, so we spent time on these because they're useful tools, and also because they have this very useful relationship to duality. And this was the kind of the one-line summary. If you want to derive the dual of a problem that looks like f plus g, minimize f of x plus g of x, then we saw that its dual is to maximize minus f star of u minus g star of minus u. Okay, so that's why knowing the conjugates of a bunch of common functions is really helpful, because we can actually read off duals maybe more quickly now that we know this rule. We also learned a rule that had to do with composition of x with a linear function. So minimizing f of ax plus g of x, essentially the a just moves from f to g in the dual. So we get an a transpose u in the dual. You can check out the slides for that precise relationship. Okay, so just jumping completely over to an unrelated topic. You're going to see it's unrelated now to duality, but as we move into interior point methods, you're going to see that second order methods are actually very intimately related to duality. So we'll get there in just a little bit. We're going to consider the same problem we considered when we talked about gradient descent. Okay, just smooth, unconstrained convex optimization. So this simple problem minimizing f of x. And we're going to assume that f has two derivatives now. And let's say for simplicity, its domain is all of Rn. So gradient descent, which hopefully you guys remember, is this method's very simple. We just compute the gradient at every iteration, and we move in the direction of the negative gradient. So we update our iterate x by moving in by some amount t times the gradient of f at x, the negative gradient of f at x. And Newton's method, which we'll talk about today, by comparison, it has a fairly different form. This is actually called pure Newton's method. Okay, so there's no step size here. I've just gotten rid of the step size. We've taken equal to 1 for now. And you can see instead of just moving the direction of the gradient, I actually move in the direction of the Hessian inverse the gradient. So it gives me a different update direction entirely. Okay, Hessian inverse the gradient. This thing's a matrix, right? So this is itself a new direction. So what's the motivation or interpretation for that? Let's go back to the motivating quadratic approximation we use for gradient descent. So we said that if I'm minimizing some convex function, right, at any point I can think about making a quadratic approximation to my function, which would be this quadratic up here, okay, at a particular point, like at the point x. And gradient descent takes this quadratic to be of the form, this form right here in the slides. Okay, as a function of y, this is the point x, this quadratic, my quadratic approximation, it looks like what's on the slides, just f of x plus the gradient of f at x transpose y minus x plus 1 over 2t times the norm of y minus x squared. So this quadratic is actually very simple. It has spherical curvature, right? It's kind of spherically shaped, and this t determines how curved it is. Okay, and if we were to minimize this quadratic approximation over y, this quadratic approximation, it gives us a new point, which we'll call x plus, and that's where we move to next. So gradient descent was motivated in this way, and it turns out that minimizing this quadratic gives us exactly the gradient descent update, just x minus t grad f of x. Newton's method, in a sense, starts off at the same point, but uses just a better quadratic approximation. Right? This really does not reflect any of the problem geometry. This simple kind of quadratic term, it's always spherically shaped, and it's just more or less curved depending on t. Newton's method plugs in what we would see in like a second order Taylor expansion of our function. So instead of seeing 1 over 2t times y minus x squared, which we can think about as approximating, if we approximate the Hessian by 1 over t times the identity, that just gives us 1 over t times y minus, this should say x, y minus x squared. Right? So Newton's method actually replaces this with a Hessian of our function itself. So in that sense, it's much more specialized to our problem's geometry than just using a kind of generic spherical quadratic form here, the 1 over t times identity. Okay, and you can check, right, that minimizing this quadratic approximation exactly gives us the Newton update. Okay, this is just a quadratic in y, so if we take this quadratic approximation given to us by Newton, and we take the derivative with respect to y, or the gradient with respect to y. Let's call this q of y. Take the gradient of q with respect to y. I'm just going to get the gradient of f at x plus the Hessian times y minus x. And if I set this equal to 0, to minimize it, it's a convex quadratic, you can see that I just am going to get y equal to x minus Hessian inverse the gradient. Right, just multiply both sides by the inverse of the Hessian and then move y to the other side. This is what I get. Okay, so it's a very basic interpretation of Newton's method. And I'll illustrate on a very simple example what this looks like. I think it's actually quite interesting to see just how different this can be. I chose this function to minimize in 2 dimensions. 10 times x1 squared plus x2 squared, this whole thing divided by 2, plus 5 log of 1 plus e to the minus x1 minus x2. Okay, so this thing is quadratic, so it's convex. This thing is, we know that log sum of exponentials is convex, right? So this whole function is convex. I had to choose a non-quadratic function for this example. So that's why I added this piece here. Why did I have to do that? Yeah. Right. So if the function was quadratic to begin with, then Newton's method would be done in 1 step, because the gradient would be linear in the optimization variable, right? And so this Newton step is going to give us the exact solution. This is the exact solution if we started, let's say, at 0. Okay. So that's why I added this term. And I'm plotting for you the contours of this function, which they kind of look like a quadratic, because this is not having a huge influence on the curvature. It has some. You can actually see, you can see it if you look very carefully. It's not exactly symmetric with respect to this kind of diagonal axis. And I'm plotting gradient descent in black and Newton's method in purple, or I guess it appears as purple, but it's blue on the slides. And I actually tune them so they take roughly the same step lengths. Okay, so in this example, I had Newton's method try to take steps that were roughly of the same length as gradient descent. So I actually did use a step size here, which we'll cover in a little bit. That was just to make this a fair comparison in some sense. Or a comparison where we could compare what they did after each iteration. So gradient descent, okay, it takes a path like this. One thing about gradient descent that I guess we never explicitly mentioned, but it is a fact, is that it's going to move orthogonal to the contour lines of your function. Why is that? It's because at every step it moves in the direction of the negative gradient. And the contour defines a constant value of the function, right? The set of x for which the function value is constant. The gradient is actually orthogonal at any point to any contour. If I ask for the gradient, at any particular point, it points orthogonally to the contour. If I take the tangent of the contour line there and I look at the normal to that tangent line, that is the direction of the gradient. And since we're moving in the direction of the negative gradient, it's moving inward towards the minimum. So this is a predictable path for gradient descent. It's just going to move orthogonal to all of your contour lines. This is Newton's method. Okay, it's completely different. We've chosen a completely different direction at every step. And with respect to this problem, it makes a lot more sense, right? We seem to be getting at the minimum a lot faster. So we're going to see this is not somehow a special example in any sense that Newton's method has a much faster convergence rate than gradient descent. Again, somehow because it's really adapts to the curvature that is implicit in your Hessian. It's not just using a generic notion of curvature. So here's the outline. We'll talk about some more interpretations of Newton's method and some of its properties. We'll talk about backtracking for Newton, so how to run Newton with step sizes. We'll go through a convergence analysis, and I'll probably present some part of the proof. And we'll talk about equality constrained Newton. And then if we have time, it's actually not that important because we'll have a whole lecture on quasi-Newton methods. I'll just give you a preview of quasi-Newton, just kind of a little bit on quasi-Newton. But we'll have, as I said, a whole lecture on that. So if we don't get to it, it's not a big deal. So let's start off with historically kind of the way Newton's method evolved, and another use of the term Newton's method that is in a sense equivalent to what we're talking about now. Let's suppose I gave you a system of equations, f of x equals 0, and f is some nonlinear function. So Newton's method arose originally to solve such nonlinear systems. Okay, and it just so turns out that Newton's method in optimization is the application of this idea to the problem in which f is the gradient of our function. right? Because if f is a smooth convex function, then minimizing it is the same as setting its gradient equal to 0. So solving this, this system is the same as minimizing our function. So Newton's method, it works as follows. Okay, let's suppose this is my function f, and I want to figure out its roots. Okay, or its root in this example. So I pick a point x, and I make a linear approximation to my function. Okay, so I'm going to approximate f at a point y by f at x plus f prime at x times y minus x. Okay, I guess in the slides I used df instead of f prime, but they mean the same thing. This is just the derivative of my function. If my function is multivariate, it's the Jacobian matrix. Okay, and then I actually solve for this function being equal to 0. I solve for its root. Okay, and what you end up getting is that y should be equal to x minus f prime of x inverse f of x. That's what happens if I solve this approximation. This is just a linear function set it equal to 0. So it brings me to some point here, which is y. Okay, and then I repeat the same idea. I take a linear approximation of my function, and I set it equal to 0, and already I'm very close to the root. So it's just the iteration. It's just these iterations repeated. That's kind of Newton's method for nonlinear, for finding the root of a nonlinear system of equations. And okay, if you just take this and you apply this to our case, you'll see this is exactly Newton's method that we've talked about for minimizing a function little f. Right, we get in this case y equals x minus, so the Jacobian of the gradient is just the Hessian. The derivative of the gradient is the Hessian. So it's the Hessian inverse our function. Our function is the gradient. Okay, so Newton historically worked on this to come up with an algorithm for looking at the roots of polynomial equations. So people and at that time were really interested in trying to characterize the roots of polynomial equations, and this is where Newton's work originated. So sometimes you might hear it called Newton-Raphson, because Raphson also worked on this problem. We never hear about Simpson, but it was only almost 100 years later, or maybe less than that, 60 years later, that this was actually applied to optimization. So Newton's method in this form. So general kind of nonlinear equations beyond polynomials and minimizing a function by applying this to the gradient of the function. So even though it's named after Newton, it actually really kind of was a bunch of people who had contributed to this. So there's a very important property of Newton's method, and that's that it's affine invariant. This is a distinguishing property between Newton's method and gradient descent. And the property is maybe precisely as follows. Suppose you're running Newton's method on, instead of running it, let's say, on f of y. Okay, so let's suppose I have some function f. Okay, and you give me a non-singular square matrix A. And I defined a function g by f of a of y. So I'm going to actually run Newton's method in some sense in a different parametrization. Okay, so it turns out that Newton's method on f and Newton on g are exactly equivalent. The iterations don't change at all. Iteration by iteration, they're the same method. And that's true, actually, if this was not a linear transformation but an affine transformation. If I added a b here, ay plus b, I would still see that the Newton on G and Newton on F are the same method, which is why we call it affine invariance. Okay, and the proof for that is actually very simple. It just uses the chain rule. So let's just look at the Newton step that we would take on G and check that it's the same as the Newton step that we would take on F. So on G, right, we would do y plus equals y minus the Hessian inverse of the gradient. Okay, let's use the chain rule now. The gradient of G, if G was F composed with A, is just A transpose the gradient of F at AY. Okay, so that explains this piece. And the Hessian is A transpose the Hessian of F at AY times A. This is just two applications of the chain rule, one to the gradient, one to the Hessian. Okay, and because A is non-singular now, right, if I have, let's say, A transpose Hessian A whole thing inverse, I can write that as, let's say, A inverse times the Hessian inverse times A transpose inverse, right? I'm just using now this property that if I have two invertible matrices, A and B, that this is true. Just applying it to this term. And I have A transpose inverse then on the right side times A transpose, and they cancel. Okay, so the updates look like y minus A inverse times Hessian inverse of F at AY times grad of F at AY. And if I ask for what that looks like after multiplying by A, which would put me back on the original scale of my variables, right, x, I can multiply both sides by A. And that says that AY plus is equal to AY times this update. And now you can just recognize that every appearance of AY I can replace with x, and every appearance of AY plus I can replace with x plus. That gives me exactly the Newton update on F. So that means that in practice, whenever we apply Newton's method, it's completely independent of the kind of coordinate system. Its progress is independent of the coordinate system we're working in. If we took our problem and multiplied it by some matrix and shifted our optimization variable, so did some arbitrary affine transformation, the progress at every iteration of Newton's method is exactly the same. That is definitely not true of gradient descent. Right, so one thing we saw about gradient descent is that it's very strongly affected by poor conditioning. So it really matters somehow what the curvature of your problem is for gradient descent. It's not invariant in some sense to this at all. And for gradient descent, if we knew that we could multiply the optimization space by some transformation that improved the conditioning, right, then we would do that, and that would actually improve greatly its convergence. That's called preconditioned. That's actually called preconditioning gradient descent. So that itself is something that is a big topic of interest in gradient descent. In Newton's method, that doesn't matter at all because we see that actually it's completely invariant or equivariant to the coordinate system. Okay, one other thing that I wanted to define is something called the Newton decrement, which is a kind of a helpful thing to know about for Newton's method. So the Newton decrement we can define any iteration of Newton's method as the gradient transpose the Hessian inverse of the gradient. That's the square of the Newton decrement. So actually the Newton decrement is just the square root of this quantity. And you can think about it motivated in a few ways. This slide motivates it in a slightly different way than the next slide. So you can motivate it as it's the difference between, let's say, f of x at my current iteration x and the minimum of the quadratic approximation I've made around x. Right? So we already actually did this calculation. Minimizing this over all y gives me the Newton step. If you plug in that value of y, if you plug in the Newton step and I look at the difference between x and the minimum of its quadratic, okay, then that actually turns out to be exactly the square of the Newton decrement divided by 2. So to the extent that we think that these quadratic approximations, let's say somehow they're reasonably accurate, we can think about this Newton decrement as an approximate duality gap, or really suboptimality gap. So if we check this and it's getting small, then we certainly know that we're, like roughly speaking, the method is close to converging. Maybe even more roughly, we could think about this as a suboptimality gap. So this is like an upper bound on the difference between where we are in the solution. Okay, slightly different interpretation is that it measures the length of the Newton step with respect to a norm induced by the Hessian. So this is the Newton direction, right? So at every step, I can think about Newton's method as moving in a particular direction, v. Right? For us, v is the Hessian inverse the gradient. For gradient descent, it's just the gradient. And I can think about the Newton decrement as measuring the length of this step in a norm induced by the Hessian. So in general, if I have, let's say, a matrix A, I can think about defining a norm in terms of A by taking x transpose AX. And what we would get if we took the norm of V as measured by the Hessian, right? So what would that mean for the norm of V if we took A to be the Hessian? That would be grad f of x transpose Hessian inverse Hessian inverse grad f of x. And just canceling, let's say, this pair, this is exactly the square of the Newton decrement. So we can think about it as when this is getting small, we're saying that actually our steps are getting small with respect to some particular measure of distance that is induced by the Hessian. Okay, so one nice property, for example, of the Newton decrement is that it's affine invariant just like Newton step themselves. So that's a reason why people like it. This notion of the steps are getting smaller because it uses the Hessian and it's not just kind of plain Euclidean distance. It's also affine invariant. So let's talk about backtracking. So far what we've talked about is called pure Newton's method. And it's not hard to see, just pulling up examples on your computer, for example, that this does not need to converge in general. So running Newton's method with a step size of 1 is not a globally convergent method. It's not always going to converge no matter where you start. So in practice, everybody uses what's called damped Newton's method, which is just Newton's method with step size optimization. And we're going to see actually a very interesting thing when it comes to the convergence analysis, that pure Newton's method is convergent, and it's actually rapidly convergent if you are close enough to the solution. So this dampening, which means taking step sizes that are smaller than 1, it's really only important to do at the starting phase of your algorithm, when the iterations are kind of starting off. Okay, so damped Newton's method is just taking, it's actually this update, I already wrote it down, with some t that's less than 1. And one nice thing about the scale of Newton's method is that in backtracking, we kind of always know what, let's say the biggest value of t that we should be taking is. That's 1. So we can always, let's say, try taking a step that's unit length in terms of this multiplier t. And then we can backtrack from there rather than starting at some arbitrarily large initial value as we had to do with gradient descent. So backtracking it's really the same backtracking that you saw with gradient descent. It's in fact the exact same exit criterion. The only thing that changes is that this v is now Hessian inverse the gradient. Or negative Hessian inverse the gradient. It's not just the gradient or the negative gradient as it was in gradient descent. So we choose two parameters like alpha and beta, and we check this exit criterion, which compares our progress to the progress of a particular linear extrapolation of our function after we've degraded the slope by alpha, some fraction less than 1. So it's the same kind of logic, right? If we're trying to minimize our function, we'll take a linear extrapolation of our function, and we'll say, how well is that thing doing? And we can't possibly hope to achieve that because for a convex function, If I take the tangent line at any point, it's an underestimate of my function. So I degrade its slope by some amount alpha, right? And I say I want to be doing as well as somehow this line, and I continue with the backtracking until that's met. Take the largest step size, let's say, possible until that's met. Okay, so that's backtracking, just as you saw for gradient descent. So here's an example. Let me give you an example that's bigger than that it's really small two-dimensional example. I'm going to run logistic regression. And again, I can't run least squares regression. I can't solve least squares regression. Because if I try that with Newton's method, the comparison's over after one iteration, right? Because the gradient is linear in my parameters, say in beta. So if I were to take the Newton step, it's equivalent to setting the gradient equal to 0 and getting the exact solution. So that's why we have to be looking at non-quadratics. Otherwise, the comparison to gradient descent, there is no comparison, right? Newton's method's done in one iteration. So here's a logistic regression example with 500 samples and 100 features. And I'm comparing Newton to gradient, and I'm letting them both use backtracking. So they're both taking as large steps as they can. Okay, and after, this is like about 6 iterations. Newton's method is at about 1 to the minus 10 in terms of suboptimality gap. And then the number is so small at the next iteration that I didn't report it. Right? It's like way off the plot. So it's converged in 6 or 7 iterations to an extremely high accuracy solution, past 10 to the minus 10. And this is the convergence of gradient descent. Okay, so it's much slower in comparison. This is on a log scale. So we see a straight line on a log scale, so this is what we call linear convergence for gradient descent, right? Which actually means that it's converging in terms of iteration. So I'll just draw that for you. So gradient descent is converging at c to the k for some c less than 1 in this problem. Okay, what Newton's method is doing is something like this, which looks different. So it looks like a different regime of convergence. What do you guys think in terms of k? What would you guess that this convergence is? So it's better than c to the k. I'll tell you, for Newton's method, c is a half. Okay, so it's a half to the something. Just guess. I think most people are kind of surprised when they hear the answer. Just it's called, I'll tell you, it's called quadratic convergence instead of linear. Okay, so k squared was a suggestion. That would certainly be faster than 1/2 to the k. It's actually 1/2 to the 2 to the k. Okay, so that's what quadratic convergence means. So it's extremely fast. It's an entire other regime of convergence. And here's the analysis. So yeah, so we're going to go through the analysis carefully. You'll see exactly what we assume. So we're going to assume, just like we did with gradient descent when we looked at its stronger convergence rate. So the stronger convergence rate of gradient descent, the one we got here, which gave us this linear convergence, okay, it assumed that our function was Lipschitz, had a Lipschitz gradient, and it was strongly convex. Okay, we're going to assume one more thing here, that the function's Hessian is itself Lipschitz. So I'll tell you that with gradient descent, this doesn't change anything. With this extra assumption, does not improve the gradient descent convergence analysis. So this amount of information just does not help gradient descent. But this is important to our analysis for Newton. The Hessian is itself Lipschitz with parameter m. So what does that mean? Let me tell you what that means. That means that if I look at the Hessian at x and I look at the Hessian at y, 2 different points x and y, okay, then the norm of this in some norm has to be bounded by m times the distance between x minus y. That's what Lipschitzness means. Well, these are matrices, right? So we have to choose some norm on matrices. We're going to use the operator norm. Okay, it actually doesn't really matter somehow what we choose, but it just makes the analysis convenient. So this is the largest eigenvalue. Okay, so the operator norm between the Hessian and x, Hessian and y, is bounded by m times x minus y. This is what it means for the Hessian to be Lipschitz. Here's the theorem. It reads actually slightly more complicated than the gradient descent theorem because there are actually two stages for Newton's method. There's something that is called the damped phase, and there's something that's called the quadratically convergent phase, or the pure phase. In the damped phase, so there's two phases for Newton's method, backtracking actually returns a value strictly less than 1. So backtracking is crucial, because if we didn't have it, I claim that Newton's method wouldn't converge, at least not in general. And when we start choosing these step sizes that are strictly less than 1, Newton's method converges kind of slowly. At every iteration, okay, so just look at this top condition here. We just gain an amount gamma on the criterion difference. Right? So if I'm looking at the criterion difference at iteration k, it's where I started minus gamma times k for a bunch of iterations k. And that is true up until some iteration number k0. After k0, we enter a second phase of convergence for Newton's method, where backtracking actually would always quit at the very first iteration. So it's always going to choose a step size equal to 1. It's happy with that. It meets the backtracking exit criterion. And in that phase, Newton's method is rapidly convergent, and it has this convergence rate that I wrote down for you. Okay, so after that iteration number, it converges like 1/2 to the power of 2 to the power of k. Okay, so this is actually what we call a local quadratic convergence rate, because we only get this quadratic convergence after so many iterations, and then it kicks in. Okay, this amount gamma that we gain on a criterion at every iteration, it relates to a bunch of properties of our function, like for example, its strong convexity parameter and the Lipschitz constant of its gradient, and it relates to the parameters we use for backtracking alpha and beta. And there's this important quantity eta we're going to see in the analysis, which is a kind of an upper bound that we use on the gradient to determine whether or not it's in the damped phase or the pure phase. And that's this parameter eta is also defined in terms of our problem parameters. You can think about it like it's some constant that's smaller than m squared over capital M, where m is, remember, the Lipschitz constant of the Hessian. And k0 is just notational. It's the time at which we enter the quadratic convergence phase, okay, which is phrased as our gradients start looking smaller than eta. So here's a bit more detail, and I'm going to sketch out actually the proof of of this kind of where this comes from right now for you guys, so you can see where that comes from. There are two phases, as I said, and they're determined by this constant eta. Remember, eta is precisely defined here. Okay, but you can think about it, it's just some constant that's problem specific that's smaller or equal to m squared over capital M. M is the strong convexity constant of our function. M is the Lipschitz constant of its Hessian. The damped phase occurs when our gradients are big. They're bigger than or equal to eta. And in that phase, we can show that at every iteration, we gain minus gamma. So we just decrease the criterion by a constant. Okay, this is a bit of a pessimistic view, but it's what we can show in terms of the convergence analysis. The pure phase, or the quadratic convergence phase, it occurs when our gradients start getting smaller than this constant eta. And once that happens, backtracking will always select a full step size, which we call the pure Newton. And we get this inequality of our gradients. This is actually where the term quadratic convergence comes from. It's exactly this inequality. So if we look at our gradient multiplied by some constant, doesn't quite matter, at iteration k plus 1, it's less than or equal to the square of that same quantity at iteration k. So this is where the term quadratic convergence comes from. And it turns out that this is what leads to this, where I wrote down, this type of convergence rate. And I'll sketch out the details for you just now. Okay, one thing that I'll just note, which I won't go into detail about on the paper, but I'll just note here, is that once you enter the pure phase, once these gradients are smaller than eta, you won't ever leave, because this condition actually implies that for all future iterations, they will remain smaller than eta. If you just look at this condition, you plug in eta here on the right-hand side, and you rearrange to see what kind of bound that gives you in the gradient at iteration k plus 1, it's going to give you something that's less than eta still. It's because eta is smaller or equal to m squared over m. Okay, so that is really just to tell you that these conditions are, they're a dichotomy. You're either in the damp phase for some period of time, and then you're done, and you're in the pure phase for the rest of the algorithm. Okay, so what I'm going to sketch out for you is just kind of the end of the analysis. The analysis is somewhat more intricate than that for gradient descent, but the end, I think, is interesting, and we can do it hopefully without too much pain right here. Right. Let's assume that we're in the pure phase, and backtracking gives us t equals 1. Okay, so this part of the proof I'm not going to do for you. I think it's longer and less interesting, or maybe it's just it's less easy to see. So there's a bunch of facts now that we're going to state and then prove. This pen is dying. So the first fact that I'm going to state for you is actually nothing to do with Newton's method. I'm just going to recall a general fact about strongly convex functions that's very useful here, which you've already seen, but I don't think we ever proved. So if f is m strongly convex, then at any point x, okay, the difference between f of x and the minimum of f is upper bounded by 1 over 2m times the norm of the gradient at f of x squared. That's an important fact about strongly convex functions. The size of their gradients, in terms of Euclidean norm, very precisely controls how far we are away from the optimum. And this is important for this analysis because we're going to be talking about how fast we can decrease the gradient in Newton's method. And then we're going to invoke this at the very end to get a suboptimality bound. Okay, fact 2. So fact 2 is going to be this one that I wrote in the slide, actually. Whatever, let me see if I get the notation correct. M over 2m squared, okay, times the gradient at any iteration, let's call it x plus, is less than or equal to the square of the same quantity. This is once I'm in this pure phase and backtracking has chosen t equals 1. And then fact 3 is going to be what we proved, in fact, is that means that if I look at for such an iteration k, after I enter the pure phase, the suboptimality gap is going to be bounded by something times 1/2 to the 2 to the k minus k0. This is the number of iterations I've been in the pure phase, right? That's why I'm subtracting k0, because I've spent k minus k0 iterations in this pure phase. And there's a constant here, I think it's like m cubed over, well, we can just look, m cubed over 2m squared. Is that right? All right, get the 2's in the top. Okay, but this isn't really so important. It's this is a constant. This is controlling how fast we converge. Okay, so let's just go ahead and prove these facts. I think we should be able to do it without too much pain here. So fact 1, I'm going to just recall that for strongly convex functions, we know that we can lower bound them at any point y by a quadratic around any point x. We proved this on homework 1, actually. This was on your homework 1. Okay, so now I'm going to minimize both sides over y and see what kind of inequality I get out. On the left-hand side, I just get f star. Right? The minimum of my function f is f star. On the right-hand side, I get something that I can compute explicitly because this is a quadratic in y. Right? And we've done calculations like this quite a bit. Right? So what I would do is I would take the gradient and set it equal to 0. So 0 equals grad f of x plus m times y minus x. And the value of y that minimizes this right-hand side is therefore 1 over m minus 1 over m times the gradient of f at x plus x. Okay, so plugged in, we're going to get that this right-hand side is equal to grad f of x minus 1 over m times the gradient of f of x squared. Right? If I plug in y minus x for this value of y, and I take the inner product with the gradient, I'm going to get the inner product of the gradient with itself times negative 1 over m. That's this. And this is similar. This is going to be 1 over 2m times the norm of the gradient squared. Okay, that just comes from plugging in this value of y in the quadratic. Okay, and that is just grad f of x. I don't know I had grad, I'm sorry. That was just supposed to be f of x. That's the first term. This is the first term. This is a typo everywhere. Just f of x minus 1 over 2m times the norm of the gradient squared. And now I just rearrange, right? The right-hand side is this. The left-hand side is f star. Rearranged, it tells me that f of x minus f star is less than or equal to 1 over 2m times the norm of the gradient squared. Okay, so that's our proof. And again, this is going to be very useful because we're going to be keeping track of gradients here. In fact, the proof, by the way, of gradient descents, convergence rate, and strong convexity also relies on this fact, and you also can keep track of gradients. So, this is just a generally useful fact when you're analyzing strongly convex functions. Okay, so that has nothing to do with Newton, but it's just kind of a good thing to see. Let's go through fact 2 now. So fact 2, remember, is this. This is the key inequality. This is what gives rise to quadratic convergence. So where does this come from? Right. So let's take a look at the gradient of f at a particular update x plus, which we know by assumption is, let's say, given by taking a full Newton update. Okay, so V is the Hessian inverse of the gradient. That's our Newton direction. This is exactly, let's say, the gradient of f of x plus v. So we're going to actually now rewrite this in a convenient form, okay, which is we're going to basically add and subtract the same term. So I'm going to subtract off the gradient of f at the point x, but I'm also going to add the Hessian times the Newton step. And you can see by the definition of the Newton step, that's just the gradient. So I've just added and subtracted the gradient. I haven't done anything. Like a hurricane outside. Okay. Thanks. All right, and now we're in a position where we're going to try to invoke some of the things we've assumed about our problem. That's what we always do in these covariance analyses, right? We have to somehow use the things that's special to our problem. And remember, we've assumed here that the Hessian is itself Lipschitz. So we're going to try to somehow write this in terms of quantities involving the Hessian, so we can invoke its Lipschitzness. So this is already in terms of the Hessian, but this is not. And this is, there are different ways to do this, but here's one, I think, kind of a simple way. We can just write this difference as the integral of its antiderivative, right? This is just using the fundamental theorem of calculus. So if I were to integrate the Hessian evaluated at x plus tv, and this was integral with respect to t between 0 and 1, I would just get the difference in the gradients. Okay, that would be, oh, sorry, of course I have to be multiplying by v because of the chain rule, right? So if I look at this, right, this guy is the derivative, let's say, of the function gradient f of x plus tv. So if I integrate it, I just get the difference of that function, gradient of f of x plus tv, evaluated at 1 and 0, which is exactly these two terms. So I can do minus the gradient of f of x at v. That's what I had before. Okay. And now I'm going to oh, here it's a plus. Yeah, thank you. So V is the negative Hessian inverse the gradient. Let's just make that clear. V is the negative Hessian inverse the gradient. So this should have actually been a minus. Okay, I'm just rearranging the terms to have something multiplied by v. And now I'm going to use, this is really, I don't know what to call it, maybe some version of the triangle inequality, where I'm going to suck the norm inside the integral, right? The norm of the integral of a function is less than or equal to the integral of the norm. And now I'm going to invoke the Lipschitz property of the Hessian, right? So this I can bound, let's say, by Cauchy-Schwarz as the operator norm of this matrix times V, the L2 norm of V. Or really, that's not Cauchy-Schwarz. That is the definition of the operator norm. Right? The operator norm gives us inequality by definition. If, for example, if you take V to be unit length, this is saying that the largest eigenvalue is exactly this. And now I invoke Hessianness of the Lipschitzness of the Hessian. This thing is less than or equal to m times the difference between, let's say, this point y and this point x. But that's exactly t times the norm of v. That's the difference between these two in norm. And I had another v, norm of v here, so that's norm of v squared. Okay, and continuing on with the inequality then, we've shown that this thing is less than or equal to m times the norm of v squared times the integral of t from 0 to 1. This is just a half, right? It's just a half times m times the norm of v squared. And let's remember what v was. V was the negative Hessian inverse the gradient. The negative doesn't matter since we're putting it inside of a norm. Right? And now we're going to use strong convexity. So I can write this again as, let's say, the operator norm of the Hessian inverse times the gradient of f of x squared. The norm of the gradient of f of x, this is actually squared, f of x squared. And strong convexity tells us that the smallest eigenvalue of this Hessian is uniformly bounded over all x by m. And therefore, the biggest eigenvalue of the inverse Hessian is upper bounded by 1 over m. Right? Because the inverse of a matrix and a matrix, they have reciprocal eigenvalues. So this thing, which is the biggest eigenvalue of the inverse, is going to be bounded by 1 over m. And since we're squaring it, it's 1 over m squared. So we get m over 2m squared, norm of the gradient squared. Okay, so we're essentially where we want. We've proved that the gradient at one iteration in 2 norm is less than or equal to something times the square of the gradient in the previous iteration, which is, if this is less than 1, right, this is a rapid decrease once this gets very small. It means that gradients get small very quickly. And if we were to, if we want to establish the inequality that we stated up here, we just multiply both sides by m over 2m squared. Okay, we just get m over 2m squared times the gradient at the next iteration is bounded by the square of this same quantity at the current iteration. Okay, so that was our proof of fact 2. Just because we're on a roll, I'm going to prove fact 3. I know that we're late for our break, but I promise I'll give you it after this. This is what's part is shorter. So proof of fact 3. Okay, so what we've established is this. Let's go back to writing things in terms of iteration numbers. The gradient of f at, let's say, iteration k is less than or equal to the same quantity squared at iteration k minus 1. And let's just call this, for convenience, AK. Okay, then we've proved that AK is less than or equal to AK minus 1 squared. That's the kind of inequality that we've produced. This is a quantity that's going to determine how fast the algorithm is converging. Okay, so iterating this inequality, right, we learned that actually ak is less than or equal to ak minus 2 to the power of 4. Right, because ak minus 1 is less than or equal to ak minus 2 squared. So ak minus 2 squared is less than or equal to ak minus 2 to the power of 4. Now you can see where the powers of 2 start to appear. This is less than or equal to a at iteration k0, once we kind of iterate this inequality, to the power of 2 times k minus k0. That's because we've applied this inequality k0 times. Each time the power of 2 has been multiplied by another power of 2. And let's plug back in for what these quantities mean. We get m over 2m squared times the gradient of f at iteration k is less than or equal to m over 2m squared times the gradient of f at iteration x k0 to the power of 2 to the k minus k0. Okay, but what do we know about iteration k0? At iteration k0 was when these gradients started to become small. Right, that was somehow what determined this new phase. I can't spell but at k0, we know that the gradient of f of x at iteration k0 and 2 norm was less than eta, this parameter eta. And this parameter eta, I don't know if you recall, but I said that it was actually less than or equal to m squared over m. That was an important property of that parameter. So take a look at this then. Okay? This whole thing is less than a half. Right? So we've shown that m over 2m squared times the gradient f of x k and 2 norm is less than or equal to 1/2 to the power of 2 to the k minus k0. That's where the half comes from. And now, as I said, we've been tracking the gradient the whole time. We're just going to invoke this fact about strongly convex functions to relate this back to the criterion gap itself. So finally, we learned that f of xk minus f star is less than or equal to 1 over 2m times the norm of f of xk squared. Right? We're going to use this upper bound. Oh, I think I have a typo. There should be a +1 here, though it's really not a big deal. In the notes, I have a typo, but it just changes this by a tiny amount. So this is 1 over 2m times 2m squared over m squared times 1/2 2 to the k minus k0 plus 1. This is what happens when we square this term. We get a +1. And I just carried this over to the other side to upper bound the norm of the gradient. Okay, which this gives us our final convergence rate bound, which is what we had in the notes. It's just 2m cubed over m squared times 1/2 k minus k0 plus 1. Okay. So that's where the convergence of Newton's comes from. We only did the end of the proof. Let's take a break. I'm sure you guys are all a bit tired, and we'll come back and talk about more properties of Newton. I just corrected the slides, but it doesn't change anything. This is still, exponentially small, or quadratically exponentially small, whatever you want to call it. So I just corrected that. So let's unravel this result and phrase it in a slightly different way. I think you're probably not going to remember this. Most people don't remember 1/2 to the 2 to the k. I think it's surprising when you see that written down, but most people at least don't speak about Newton's method in that way. Most people use epsilon suboptimality when they talk about Newton's method. And let's flip that around. So let's ask, for a particular epsilon, how many iterations k do I need to get the suboptimality gap less than or equal to epsilon? Okay, remember that gradient descent required, in strong convexity case, log of 1 over epsilon, which was a lot faster than 1 over epsilon, which was its rate without strong convexity. So even that we thought was great. Log of 1 over epsilon is really small, right, to get high accuracy solutions. Newton's method, okay, it requires some number of iterations to get into the quadratically convergence phase. That's this number. Right? If we decrease the criterion by gamma at every iteration, then we need at most this number of iterations to get into the quadratically convergence phase. Because after this number of iterations, we're going to start making the criterion difference negative, which we know is not possible. We can't get better than f star. So this number is just the number of an upper bound number of iterations we need to enter the pure phase, quadratically convergence phase. This number is what we get by setting this term equal to epsilon. So set, let's say just call it maybe c times 1/2 2 to the k minus k0 plus 1 equals epsilon. And if you solve for epsilon, you're gonna need to take 2 logs, right, to get this k down after it's up 2 exponents. And you'll see that you need k to be log of something over epsilon. That something's another constant, which doesn't really matter. Or maybe we should just say you need k minus k0 to be this number. This is how many iterations you need in the quadratically convergence phase. Oh, I'm sorry, I was not showing that to you. Right, so I just need to make this many steps in the quadratically convergence phase. And an upper bound on k0 was this thing right here. So it's really log 1 over epsilon that people remember. That's the rate everyone cites for Newton, which is also called quadratic convergence. We're emphasizing that this is actually a local rate, so it doesn't give you the global convergence rate Newton method. It actually tells you how fast it converges once you're close. And actually, the global rate for Newton's method, somewhat disappointingly, is actually, I believe, it's just linear. So globally, if you look at like the worst case starting point, I believe you get back the linear convergence rate. In practice, the quadratic convergence phase, typically you'll see that you enter it very quickly, and so it really does converge very rapidly. And with warm starts, if you actually solve the nearby problem beforehand, and you now warm start your algorithm, you can enter the quadratic convergence phase very quickly. And that is, in fact, what interior point methods do. They are designed so that you never leave the quadratic convergence phase. That is the beauty of interior point methods. Somehow, like, it's running Newton in a sequence where you never leave quadratic convergence. You're always in it. So that's just maybe a comment about this local versus global rate. One other comment is that some authors actually, in particular Steve Boyd in his book, they actually say that log 1 over epsilon is a constant. It's not even a function of epsilon. It's just 6. Because realistically, let's say these logs are base 2, right? You wouldn't really want to be asking for accuracy beyond 1 over 2 to the 2 to the 6. Right? That's like beyond numerical accuracy stored on a computer. Like you couldn't even measure somehow if you were. So 2 to the 2 to the 5 is 2 to the 32. Right? So 2 to the 2 to the 6 is 2 to the 64. Unless you're using like somehow, not standard double precision, unless you have some other considerations, you couldn't even measure whether you're converging faster than that. So you can think about the number of iterations Newton needs in practice to be like 5 or 6. And all right, so one thing that's actually quite important to point out is that there's actually a bit of a contradiction between what we just did in the proof and what we saw with affine invariance. So we just said that the method itself does not depend on affine transformations, right? So if the largest eigenvalue was of the Hessian was L, and the smallest eigenvalue of the Hessian was M, right, then maybe there's some linear transformation that we could use to change those. I would get maybe better conditioning. So what we see from this slide is that actually that doesn't matter. Like it's possible that our function is poorly conditioned, so that L is very large and M is very small. But it shouldn't matter, because if I multiply by a linear transformation that brought that conditioning to be better, so it brought the condition number closer to 1, the method's the same. What that tells you about Newton is that actually it shouldn't depend on L or M. These quantities should not appear in our convergence analysis. Right? These quantities that involve conditioning, they're not going to affect the algorithm empirically, but yet somehow they're in our convergence analysis. So this bothered people for a very long time about Newton's method, that somehow we didn't have a satisfactory scale-free analysis of Newton's method that was just saying universally, here's how well it does. And this was, I think, a very important development optimization due to Nesterov and Nemirovsky, who invented a concept called self-concordance. And I think it's a very beautiful topic, but really it's most used in interior point methods when we talk about self-concordant barrier functions. And that's just, it turns out to be kind of a technical thing that was an important development, but now is kind of folded into standard technology. So as a result, kind of we all benefit from self-concordance in the design of these barrier functions and interior point methods, but we don't really worry about it so much. So I'm not planning on going through any details, just telling you what it is and telling you that if you have a self-concordant function, then the analysis of Newton's method is actually universal. It doesn't depend on these conditioning quantities. A self-concordant function, it has a bizarre definition, but the way you can remember it is by remembering that the canonical self-concordant function is minus log of x. Okay, and then take 3 derivatives of minus log, take 2 derivatives, and you'll see that they're related by this. You actually get an equality here. So a self-concordant function is a function that's convex and has 3 derivatives, and its third derivative in norm is less than or equal to 2 times its second derivative to the power of 3/2. And I said this is kind of a bizarre definition, but you'll see that this is motivated by the negative logarithm. It gives you an equality here. And if you have a function that's on Rn, then we call it self-concordant if you look at it along every line segment. And that univariate function meets this definition. For self-concordant functions, okay, there's this very beautiful development due to Nesterov and Nemirovsky. And this pours over into interior point methods, as I mentioned, that tells you that the Newton's method, with the same considerations, backtracking line search with parameters alpha and beta, it takes exactly this number of iterations to converge, no matter the conditioning of f. Some constant that's universal, it just depends on alpha and beta, your backtracking choices, times the gap where you started, plus log 1 over epsilon. Okay, so this does Newton's method justice in the sense that the analysis does not depend on properties of its gradient or Hessian, like Lipschitzness or strong convexity. Some examples of self-concordant functions are here. I don't think that at this point it's really so important to go through, but there's a lot of literature if you're interested. So let me do a comparison to first-order methods. I didn't get to equality constrained Newton, actually. It looks like we ran out of time. So I'll have to do that next time. We'll just go through this comparison, and then we'll quit. Let's do a very high-level comparison on many axes to first-order methods. What does memory look like? Memory usage look like between Newton's method and gradient descent? Well, in gradient descent, you only need to store the gradient, right? Once I'm somehow evaluating the gradient, I just have to store n numbers, and I get to move in that direction. Okay, in terms of Newton's method, I actually have to store the entire Hessian. In the worst case, the Hessian is dense, so that's actually order n squared things you have to store. It's quite a bit more expensive memory-wise. And for large problems, it's actually both memory and computation that can kill you with Newton's method. Okay, computation is an even more drastic difference. So every step in Newton's method requires computing this direction, right? Hessian inverse the gradient. This direction v. Hessian inverse the gradient. So said differently, this requires solving a linear system, which is the Hessian times v equals the gradient. If this Hessian is arbitrary, so it is dense and not structured, which is often the case, depending on your problem. It can be very often the case that the Hessian is just an arbitrary dense matrix. Then that requires on the order of n cubed computations, right? Solving a dense linear system is like n cubed operations. And that's a lot more expensive than order n, which is the cost to move in the direction of the gradient, right? I'm assuming that the computation of the gradient itself is not more expensive than linear either, which is typically the case. Okay, backtracking has roughly the same cost for both. Newton's method, fortunately, you just fix v and you look at backtracking. You check the backtracking exit condition with the same v the whole time, so it's not more expensive. So they're the same. Okay, conditioning. Newton's method wins outright in this regard. So in practice, it doesn't matter how poorly conditioned your problem is. Newton's method accounts for that by actually, in a sense, sphering the problem by the Hessian. So it changes the coordinate system so that in the new coordinate system it's working with, you have perfect conditioning, right, by multiplying by the inverse Hessian. Gradient descent can seriously degrade for poorly conditioned problems, and then there's a whole industry that involves preconditioning to try to figure out linear transformations to change the coordinate system before you apply gradient descent in order to avoid this, which we didn't talk about. The last thing on this comparison is fragility. This is really more of a, I think it's only a kind of a semi-rigorous claim. I'm making this kind of based on experience and also based on, I think there is kind of budding literature to this effect, that gradient descent is more robust to numerical errors. So actually, I mean, for other reasons that have to do more with, I guess, statistical reasons, there are variants of gradient descent that actually add noise to the gradient. Okay, stochastic gradient descent, in fact, you can think about as it is looking at a noisy version of the gradient. So just by virtue of the fact that SGD works, and there are also other methods where we actually add, let's say, Gaussian noise to the gradient, that those things are made to work, you can just intuit that gradient descent is more robust, right? Because this is actually us adding auxiliary noise. If you have some, let's say, numerical errors in your gradient computation, that's implicit noise, but still gradient descent is going to be robust to those things. Newton's method, I think, is empirically much more sensitive to these issues. So solving this linear system poorly, so not getting a very good solution to the linear system, can actually really hurt you. Not computing the Hessian or the gradient exactly can really hurt you. It's more fragile. Quasi-Newton methods, which we'll talk about in 3 lectures from now, are a nice middleman between first order and second order methods. Okay, so they actually mitigate a lot of the concerns we have with Newton, but retain a lot of the strengths. So they're a very important thing to know about. All right, so I'm just going to go back to this one example, then we'll quit. This was the same logistic regression example. I actually parameterized on the x-axis. Now, I parameterized it by time. I just timed these in R rather than actually taking the number of iterations. And so what you saw here, okay, once I account for the difference in iteration cost, is much less drastic. So Newton still wins, but it doesn't win by as large a margin, right? At least at the start, it's kind of a wash as to how the algorithm is performing. That's just more, kind of its empirical evidence that this computation makes a difference. And this was actually not a very big problem. This was like, I think, only 100 variables. So, all right, I will see you guys on, next Monday. Today's Wednesday. I'll see you guys next week.